So data collection is one of the biggest tasks in solving a real problem, my friends. One of the most important and the difficult problems in simulation project. Remember, the most important process in a simulation project was the validation. Validation validates if your input models are correct or not. Not directly it validates the input models, but indirectly. It actually validates the outputs. However, if the outputs are not validated, most probably this is caused by the input models or the model that you design. It can be caused by many things, but most probably it is related to input models that you are using. So validation is the most important process. However, another most important process is the data collection phase. Now, before fitting an input model, accurate and problem relevant data should be available. So before you say that the inter-arrival times are exponentially distributed or the service times are normally distributed, before coming up with these results, first we need to check the data. We need to have accurate data which is measured correctly, and it should be problem relevant data. Today's advanced technologies and the systems that is provided by management information systems, such as transaction processing systems, the organizations can collect a huge amount of data about the transactions that they perform in each system. And within this huge amount, even if you have a different problem, you can definitely collect the relevant data from this huge amount of data. So if you do not have these technologies to collect such huge amounts of data, in that case, you need to focus on the problem relevant data, because data collection is a very long process and you do not want to spend so much time on it. You should be focusing on collecting the problem relevant data. And the properties of data must be very well understood. We need to understand the behavior of the data, how it is collected, and not just the data itself, not just the numerical value. We also need to understand the structural knowledge on the process itself. So from what type of process we are collecting this data? I can give you data and I do not say anything about it. So this is just the data. Find a model for me. This is not going to be the approach. I should also give you the process that is collected from. I should also give you the process knowledge that it is collected from. So I should say these are collected inter-arrival times of the customers to a supermarket. So I also need to give you this property as well. Input modeling software, my friends, for example, Arena is capable of input modeling. It's an input modeling software as well. If you just give the data to an input modeling software, that input modeling software will not say that I couldn't fit anything. It will always fit some probability model to the data. However, it will never understand the structural knowledge on the process that it's coming from. It will never understand that it is either an inter-arrival time or a service time, or it is demand of a certain product. So it does not know the structural process that the data is coming from. How can we really say that an input modeling software really identifies the statistical model behind it? So it will use an optimization procedure to fit the best possible probability model with the minimum error. However, if you do not justify the properties or the process that the data is coming from, then it may still be a very wrong conclusion. So do not rely on the input modeling software so much. Instead, rely your human brain. Now, I have told you that random numbers cannot be generated by human minds, okay? Because human mind has this tendency of bias. However, human mind is better at one thing in input modeling. It is a lot better compared to the computers. Computers are fast, so I agree on that. If you give the computers a large list of candidate distributions, then the computer is going to find the best possible model among these candidates in a very, very fast manner. However, even though the human mind is slow, human mind understands the structural knowledge of the process better than computers. Do not just rely on the software results. You need to justify the distribution based on the structural knowledge of the process that it is collected from. So we have said that data collection is important, and we know that you can transfer the data to an input modeling software, and the input modeling software can easily identify the best possible existing probability model with the minimum error and says that this data comes from this family of distributions without justifying the structural knowledge on the process itself. And I'm just going to show you a few examples now where you can easily deceive a input modeling software. If I give that data to the input modeling software, that input modeling software can easily be deceived by the distribution. So see, first, what type of problems do we have in data collection? First of all, my friends, if you are going to use data for input modeling in a simulation project, the collected data must be up to date. You should not use an outdated, or in other words, stale data for modeling. So, for example, if you are going to solve a problem related to today in a system, you cannot develop a simulation model based on the data which is collected 5 years ago. The data must be up to date, which means if you are using the simulation as a constant methodology to solve problems in a system, in that system, you should continue to collect relevant data to the problem. If the current data is not available, instead of using an outdated data, using expert opinions is much better idea, it says. So it is at least less dangerous because the experts have opinions about the up-to-date trends as well. However, stale data, outdated data do not reflect the behavior of a system. The second problem that you may observe, we should not end up with straightforward conclusions with a few statistics. For example, let's just say I have collected a data and calculated the sample mean and the sample variance. The sample mean looks like 10.98 and the sample variance is 118.27. As you can see, the relationship between the sample mean and the sample variance is what? The sample variance is almost equal to the square of the sample mean. Now, you know in which distribution you have this situation. If you remember, for the exponential random variable or for exponential distribution, the expected value is 1 over lambda and the variance is equal to 1 over lambda square. And you know, in exponential distribution, the variance is the square of the expectation. That's easy. So a straightforward conclusion by looking at the sample mean and the sample variance may be this, because the sample variance is almost equal to the square of the sample mean. I think exponential distribution is a very good distribution. This is definitely a wrong approach. It is, I mean, in a normal distribution, the variance can also be a square of the sample mean. There are other distributions in which you can define the variance as the square of the sample mean. So do not come up with such straightforward conclusions about the distribution decision. Let's check this data. The previous data, by the way. It is the continuation of the previous data. So you see, we have identified exponential distribution as a good candidate because the sample mean and the variance has this relationship. The variance seems to be the square of the sample mean. However, here we are given the histogram of the data. Okay, and when you check this histogram, it does not exactly look like an exponential PDF. You know, the exponential PDF is a decaying PDF starting from lambda and it decays to 0. And when you check this histogram, it does not look like the exponential PDF. Instead, it looks like a mixed normal distribution. There is two normal distributions here. The first normal distribution has a lower mean with a lower variance, and the second normal distribution has a larger mean and a larger variance. So remember now, this data comes from the service times. An exponential distribution usually is not a good candidate for modeling the service times. Rather, normal distribution is a better one. And then when you analyze the system further, you realize that there are two kinds of clients. One requires a service time with a low mean and a low variance, and the other requires it with a higher mean and a higher variance. So imagine a bank system. The bank is serving for two types of clients. One type of client is just withdrawing money. However, the other types of clients are trying to open a savings account. Okay? So if you intend to open a savings account, then the average time for this process is going to be large, and also the variance is also going to be large because there are many, many different things that you need to check. However, if you are just going to withdraw money, the withdrawal operation is going to take short because in the end, you are just going to take your money and you are going to get a bill for that, and that's it. So the first type of process or first type of customer is going to require a service time that has a lower mean with a lower variance. The second type of customer is going to require a service time which has a higher mean and higher variance. So it is very important, my friends, to understand the structural knowledge on the process as you see. If you just look at this data, maybe the input modeling software is just going to say it looks like exponential distribution. Do not rely on the software so much. Your brain is much more reliable. Your understanding of the process is much more reliable. If you realize that there are two types of clients, and if you realize the distinction between these client service times and their second class of client service time, then you need to define two different input models for this distribution. So first, you need to determine the type of clients, and given the type of clients, you need to develop conditional distributions which follow normal distribution for the service time of each type of client. So do not just transfer the data to the input modeling software, because in this case, you may end up with a different distribution that it's supposed to be. Now, it says analyze the data from different perspectives. So let's just say, in this example, we have data of the inter-arrival times between 11 a.m. and 10 p.m. Okay, from 11 a.m. to 10 p.m. So the shopping centers are opened approximately around 11 a.m. And until 10 p.m., there are many customers arriving to the store, and the inter-arrival times, the time between the consecutive arrivals of the consecutive customers, is observed, given in a list, and this is a histogram of the inter-arrival times. And when you check this histogram, and when you check the sample mean of the inter-arrival times and the sample variance of the inter-arrival times, the histogram looks like an exponential distribution this time, and the sample variance looks like the square of the sample mean. If you take the square of the sample mean, the sample variance seems to be equal to the square of it. Now, my friends, as I have said, you need to look at the data from different perspectives. I mean, by just looking at from these two perspectives, you may end up with a hypothesis of an exponential distribution. However, if you check the inter-arrival times within each hour, the number of arrivals within the first hour are around here. On the average, in the first hour, 400 customers are arriving. However, starting from 2 p.m. until 7 p.m., there is a rush hour, and the average number of arrivals occurring in each hour is increasing. So you see the rate of arrival, they change from hour to hour in this store. So the time between consecutive arrivals are going to be smaller from 2 p.m. to 7 p.m. Okay, in this 5 hours, we have rush hour, and the average number of customers arriving per hour are 500. So the inter-arrival times are time varying. So if you just look at these two pictures, you will say that on a single day, inter-arrival times follow exponential distribution with rate equal to 1 over 0.14. You are just going to assume that the arrival rate is going to stay constant throughout the day. However, if you look at the data from this perspective, if you, for example, count the number of arrivals between 11 a.m. and 12 a.m., 12 a.m. and 1 p.m., 1 p.m. and 2 p.m., 2 p.m. and 3 p.m. If you count the number of arrivals, you will see that the arrival rate doesn't seem to be constant throughout the day. And this means you need to identify a separate distribution for the first 3 hours. So for the first 3 hours, you can say the inter-arrival times are exponentially distributed with rate 400 customers per hour. In the next 5 hours, again, we may have an exponential distribution, however, with rate 500 customers per hour. And in the last 3 hours, we have exponential inter-arrival times, this time with rate 300 per hour. Okay, so you see, by looking at the data from two perspectives, you still may end up with wrong results. You may also try to understand the arrival process of the customers. So these kind of things, unfortunately, cannot be performed easily by simple input modeling software. You need to develop very advanced input modeling software. The software should check the data from different perspectives and identify such conditional distributions for each hour interval. It should define a separate input model. Otherwise, you are going to create a simulation model which is totally wrong and which concludes with erroneous results. Now, another perspective that you need to check is the autocorrelation. It says check autocorrelation for time series. So if you have a data in the form of time series, then you also need to check the autocorrelation. Now, this is the histogram of the monthly demand to a certain product. So we are counting the amount of demand in, for example, tons or quantity of products in every consecutive month. So for the last 20 years, let's just say, we have collected the monthly demand to a certain product. And when you check the histogram, it looks like normal distribution, right? So it looks like this bell shape. There is a peak in the middle, and the distribution seems to be approximately symmetric. Not exactly, but approximately symmetric. So we cannot come up with strict conclusions, but the histogram is calling for a normal distribution with location parameter 325,000, which is the mean value, and the variance of the values observed in this histogram is close to 4 times 10 to the power 8. So the histogram calls for normal distribution. However, remember now, the monthly demands that are observed in the last 20 years, they form a time series, my friends. And when you check the time series, leg 1 scatter plot, which means when you plot the demand in any month with the demand in the next month, for example, starting from 20 years ago, demand in January versus demand in February, and demand in February versus demand in March. And when you check the scatter plot, you see that this leg 1 scatter plot, which is a plot diagram between the consecutive month demands, it shows a trend, right? It shows a trend. It does not show a distribution, a scatter around a constant point. Instead, we have a trend line here like this dashed red line, and the plot is distributed symmetrically around this increasing trend. So which shows that the demand in the consecutive months are not independent. So which means the demand in the next month seems to be dependent on the demand in the previous month, because there is an increasing trend in this time series. Because in the last 20 years, the average demand per month is increasing. So you cannot simply say from this point, the next month's demand is going to be distributed with the normal distribution. Instead, you need to develop a time series model for that demand. So this is not a part of this course. I'm not going to talk about forecasting models of the time series. Now, in this example, what I wanted to show is by this leg 1 scatter plot, by plotting all demands in a month with the demand in the next month, we can discover that the demand in the next month is dependent on the demand on the previous month. Therefore, when we are developing an input model, we should not behave as if all observations are independent. Instead, we should develop a time series model here. So there are a few suggestions by the authors of the simulation textbooks. They say that the input modeling requires the analyst to use judgment. Judgment, unfortunately, it's not a capability of an input modeling software. So you see in the previous problems that I have shown you, we need to use the judgment by looking at the data from different perspectives and by understanding the process that the data is coming from. This judgment, unfortunately, cannot come from most input modeling software. However, we also need to apply appropriate statistical tools. For example, we need to apply goodness of fit tests. We need to draw different descriptive statistics like histograms and scatter plots, and these kind of tools are provided by the software. Actually, the input modeling must be performed by humans. However, this does not necessarily mean that they should not use any statistical tools which are provided by software. So we need to work together. We need to work with the software in input modeling. However, we also need to rely on our knowledge and judgment as well. Secondly, another suggestion, we need to take some time to plan in how we are going to collect data. So if I tell you to collect the data about a system, and on the next day, if you go with a chronometer in your hand and watch the system throughout the whole day, this is going to be a primitive approach, okay? So do not behave immediately. Instead, you need to think of a very clever and advanced way to collect this data. For example, another idea can be what? You can record the system by a video camera, then watch it in a faster manner. You can use a computer software which can count the inter-arrival times of the customers by watching the video. Or you can use a barcode system or an RFID system to determine when, for example, a customer goes through the cashier. So you know when they are making payments, we are also creating a receipt, and the time of the creation of the receipts can give you the end of the process. So when the cashier process ends. So when you purchase from a certain store in the shopping center and go to the cashier, they first read the barcode of that product, and as they read the barcode of the product, the payment process starts. And when you take the receipt, the payment process ends. Actually, the timing of these two processes are recorded in a system. You can easily determine the cashier duration time for a single customer. I mean, because of that reason, it is not necessary for you to watch the whole process by your eyes and determine the service times. So you need to develop a very clever procedure to collect the data, okay? And you need to take your time to develop that clever procedure. You need to use the technologies such as RFID, barcodes, and other type of recognition techniques. We need to start analyzing the data as they are being collected. So this means we should not wait for 3 months until a huge amount of data is collected. As we collect the data, we should also develop an input model for that, because this is an adaptive process. So you develop a model, then you test it, and in order to validate your model, you need to collect additional data. So as you collect the data, you also start analyzing it. And try to combine homogeneous data sets. So as I have said, my friends, in this example, for every hour interval, I can develop a separate input model. However, if I develop a separate input model for every hour, then the models are going to be less reliable. Instead, you can easily see that in the first 3 hours, the arrival frequencies are similar. In the next 5 hours, the arrival frequencies are similar, and in the last 3 hours, the arrival frequencies are similar. So instead of developing a separate exponential model for each hour, I'm just going to combine this homogeneous data set here, and for the first 3 hours, I am going to develop a separate model. Just like I'm going to develop a separate model for the next 5 hours. So this suggestion here suggests that try to combine homogeneous data sets if the data sets are similar to each other in behavior, why should we develop a separate model for them? Instead, you can combine the data, and with a large amount of data, you can develop a much more reliable input model. The next suggestion suggests that we need to build scatter plots and discover the possible dependence relationships between the couple of variables. So as you can see, because the demand here is a time series, you definitely need to plot the demand of one month with the demand of the next month, or you can simply draw a plot diagram of the demands of the consecutive months, and you can easily determine from there as well, there is an increasing trend in the time series of the demand. So it is a good idea to draw not just the histograms, but also the scatter plots of the data to see if there is a possible dependence between the couples of variables. And also sometimes we need to plot two variables with each other. For example, if you plot the service times of these customers with the types of the customers, so let's just say the first type of customers are called customer 1, and the second type of customers are called customer 2. If you plot the type of customers column with the service times, then you will easily see that there is a dependence between the type of the customer and the service time in that situation. So there may be dependencies between two different variables as well, two even more, okay? So you need to discover all of these relationships as well. You need to check the correlation between couples of random observations that belong to the same person. For example, sometimes the service time of a customer may be dependent on this customer's arrival time or the service starting time. For example, until when you reach the end of the day, the cashiers in the supermarket gets less and less motivational, that they get tired, and because of that reason, as you come to the end of the day, the average service times, they can tend to increase, okay? So you need to be able to discover such dependent structures. So data collection and discovery of these relationships in the data is a very, very hard thing to do, my friends, okay? And it is just like an art. I mean, data analysis is an art. It is not just something that is technical. It is also an art. As I have previously said that the model development as art as well as it is a science, okay? It is both science and art. So we can also build scatter plots to discover the autocorrelation in the time series. If it is a time series, again, you can use the scatter plots to discover the autocorrelations. And remember now, the most important suggestion, you need to be able to distinguish what is input and what is output. So I'm going to explain this with an example. My friends, in a supermarket, the arrival times of the customers is an input because the customers are coming from outside the system, and whatever policy you can change, the arrivals, they do not usually change. I mean, in the supermarket, even if you change the location of the cashiers, even if you change the number of cashiers, the arrival times of the customers is not going to be affected from that. I mean, unless if you attract more customers. But if you do not attract more customers, in that case, the arrival times are just going to be input. Service times are also inputs. I mean, you have a control over them. However, the service times are also inputs. So you can, for example, train your cashiers, or you can use the barcode technology in payment process, or another type of technology such as RFID, and you can increase the speed of the cashier process as well. But still, the service times in the cashiers are the input of the system. So what is an output? An output is a measure, is a variable which can be computed by collecting all the inputs. So if you have all of the inputs, then you can calculate the outputs. If one of the inputs is missing, then you cannot calculate outputs. So what is an output? For example, the time spent in the system by a customer is an output, or the time spent in the queue by a customer is an output. So this output is a performance measure, and this performance measure is dependent on what? It is dependent on the arrival frequencies of the customers, the rate of service in cashiers, and the time spent in traveling by the customers in the supermarket. So it is dependent on the input variables. Okay, sometimes the simulation modelers are collecting the output data as well, and they are trying to develop an input model for the output data. So you need to understand for which variables you need to develop an input model, and what variables are going to be the results based on the input variable. So there is input data. Input data is what? Inter-arrival times, service times in a queuing system, or in an inventory system, the demand and the lead time are the input data. However, the daily closing inventory levels is the output of that system, because it is affected by the daily demand and the lead times and the deliveries. So the closing inventory level is an output. It's a performance measure. It's the output data. We are not trying to find a model for the output data. We are just trying to find a model for the input data.